Welcome to Study Loop.
Hi, so this question is asking us to determine what the nature of the octet rule exceptions are in these three species. So we'll start with BH3. We have the boron in the middle, and then the three hydrogens on either side, like so. We can draw a single bond, and this is just, remember, the basic procedure for drawing any Lewis structure. We know that boron is the only one that can form multiple bonds and must go in the middle. We then will calculate the number of valence electrons we should have, and we can do that just to verify. We look at boron here in group 13. Boron should have 3 valence electrons because it has the 2 in the s, and then the first part of the p orbital. So it's just one element in, and we'll only have 1 in the p orbital. So that's 3 total. So then we have 3 for the boron plus 3 times 1 for each of the hydrogens, and that gives us 6. And we've already taken care of that. If you see, each of the single bonds takes care of 2, so 2 times 3, 6, we're all set. The problem is that boron does not have a complete octet, and because of that, it is missing electrons, which means that boron is electron deficient. Electron deficient boron. And that's what is causing this exception where boron does not have a complete octet. All right, let's look at this ion here, which is arsenic tetrafluoride. And so once again, we know that the halogens are almost, since they can normally form only one bond, arsenic can form multiple, arsenic goes in the middle, and we can put the 4 fluorines around arsenic like so. To make sure we remember that this is an ion, I'm just going to put the bracket around it with the negative charge. We'll calculate the number of valence electrons. So arsenic is in the same group as nitrogen. It needs 5 valence electrons. So we have 5 for arsenic plus 7 times 4 because we have 4 fluorines plus 1 for the negative charge. And that's going to give us 34 total. We'll draw our single bonds in. That takes care of 8. And then we can start filling the rest in lone pairs. So that's 6 more. Now we have 12, 18, 24, and if we calculate, we see that we have 32 just with all the fluorines. But we need 2 more to get to 34, and that can go on as a lone pair on arsenic. So just looking at arsenic right now, arsenic has 2, 4, 6, 8, and 10. So it has 10 electrons. Because arsenic is in period 3, it can send some electrons into, actually it's in period 4, it's beyond period 3, so it can send some of its electrons into a d orbital and therefore have what is called an expanded valence shell. And that's the nature of the exception here. It's an expanded valence shell because arsenic has the ability to push any extra electrons into d orbitals. So it does not, even though it's in the p block, it can push electrons into the d orbital and thus exceed its octet. So it has an expanded valence shell, expanded orbital. So it basically is taking on more electrons than we expect from the octet rule. All right, the last example is selenium tetrachloride. So we put the 4 chlorides here. We draw our single bonds. We see, so for selenium is right here. It's in group 16 rather. So it will have 6 valence electrons, plus 7 times 4 for each of the chlorines. So we need 34 here as well. I apologize. Yes, 34. 28 plus 6, 34. And we have 8 taken care of here. So we need 26 to go in the lone pairs. So we do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 24. Remember, we needed 26 remaining beyond the 8 here. So that extra 2 is going to go here. And if you calculate, we'll see we have our 34 because we have the 8 in the single bonds. We have 4 sets of 6 in the lone pair electrons. That's 24. So 24 plus 8, 32, plus this extra lone pair, 34. So we're all set. Like arsenic in the previous example, selenium also has 10 electrons, which is an expanded octet, and therefore it's an expanded valence shell. That's the nature of the exception here. All right, I hope